here's what we're going to look at today. We left off with the trend on the periodic table being atomic radii. Now that atomic radii, we know that as you move across the periodic table, that radius decreases. And the reason why it decreases is because as you move from left to right, you increase in the nuclear charge. It's going to pull those electrons in closer to the nucleus. As you move down the periodic table, the atomic radii is going to increase. All right. The reason why it increases, you increase in the number of energy levels, you increase in the amount of shielding that's going to occur between that positive nucleus and that outermost electron. There's going to be an increased amount of electron to electron repulsion, so that radius keeps getting bigger as you move down it. So that was the basic idea, and we finished off looking at sodium, that 11 protons and 11 electrons, and we said that nucleus would have surrounding it 3 different energy levels. Okay, it's on the third period of the periodic table. We'd have 3 energy levels, 11 electrons, and that 11th one would be in that outermost energy level, that third energy level. So this guy right here, because we only have 1 valence electron, that causes this whole atom to be unstable. So materials, they don't like to be unstable, so what's going to happen is that 1 single electron is going to be removed. Now, that 1 single electron, when it is removed from the electron cloud, we're still going to have that 11 positive nucleus. Right? You're not changing the number of protons, but what you're changing is the number of electrons in that electron cloud surrounding that nucleus. Okay, so you'd have something like this. Now that outer electron is lost. If that outer electron is lost, now we have 8 valence electrons, and it's always great to have 8, because if you have 8 outer electrons, that means you have the S and P sublevels that are filled. That guy would be stable. Now when it forms that 8 outer electron configuration, that means that this sodium becomes a sodium ion. Okay, so we're forming an ion. What's the difference between the first drawing there and the second? In the first one, we had just a neutral atom. We had that neutral atom. And in the bottom one, we have a sodium ion. All right. So you formed an ion by removing an electron, and that is looking at the second trend on our periodic table. Okay, the second trend is the ionization energy. All right, now ionization energy, we formed an ion by removing that outermost electron. So our definition for ionization energy is it's simply the energy required to remove an electron from an atom. Okay, we should put in there in the gaseous state, but we're just going to leave it as that for right now. So we have that sodium atom. If we remove that outermost electron, there's a certain amount of energy that's needed to pull that 1 electron away. That 1 electron is not just going to fall off on its own. Okay, there is some attraction that is occurring between that nucleus and that outermost electron. That's what's keeping it there. It's unstable, but it's keeping it there. So how much energy is actually needed to remove that? Well, first, let's go ahead and take this, and we're going to put it down here so that way we can assign a number to this. All right, so that one electron right here, that one electron in that third ring, it needs to be removed. In order for that to become stable, to form an ion, we have to get rid of it. So if that's the first electron that needs to be removed, then we need to take and focus on what we call the first ionization energy. Now these numbers, you don't have to have these memorized, because on my periodic table, I give them to you. So we're trying to figure out how much energy is needed to remove that outermost electron for that sodium atom to become chemically stable. So let's take a look at that periodic table. On my table, you're going to find in the lower right portion for boron in my key there, in the lower right hand corner, it has 801. Now what that represents is 801 kilojoules per mole. That's referring to energy needed to remove the outermost electron, that outermost electron for boron. All right? Now for sodium, that's the one in question. We come over to sodium cell, and for sodium, it says that our first electron that we're going to remove, in order to pull that electron away, it's going to require us to apply 496 kilojoules worth of energy. So let's go back to our notes here. Our first ionization energy is going to require, and I forgot it, here we go, 496. All right, so we have 496 kilojoules per mole to remove that outermost electron. Now when that happens, what I'd like to do is just write down what the orbital notation for this would be. And if you recall, when we do these, you'd have the 3s1. All right, so we are taking the outermost electron, that 3s1, we're taking that electron and we're applying 496 kilojoules worth of energy to remove it. All right, now when we remove that, that is no longer with our element. And if we count up the outermost electrons now, in that second energy level, you have 8. Now, you might say, well, what's the purpose of doing that? Why are you bringing that up? Because we already know that that energy level, that's no longer there. All right, but let's just look at not the first ionization energy, because we remove that first electron. That's the 3s1 electron right there. I know this element, I just told you, was stable, but let's just say that for some reason you wanted to try to remove the second electron. All right, so let's say that we're going to try to remove the second electron right there. Would it be easier or harder to remove that second electron? Right now, this would be stable. So does it want to remove a second electron for sodium? The answer is no. So for us to try to remove that second electron, or our second ionization energy, the amount of energy that we're going to have to apply to that is going to be significantly greater than that 496 kilojoules. All right. These are numbers that you don't have to memorize, because there will be sources that we can pull from. And right here, that's that first electron that we removed from sodium. But if you look at the second ionization energy, how much more energy is needed to remove that second electron? That second electron would be forcing that sodium atom to go from a stable state to an unstable state. So there's going to need to be a lot of energy needed to remove it. And the value that's associated with trying to remove that inner electron would be 4,560 kilojoules worth of energy for every single 1 mole of sodium. So significantly more, almost 10 times as much energy is going to be needed to remove that. And you're going to see just in this chart that our first ionization energy, by comparison for all of these, for magnesium, 738, 1,450, in every one of these cases, it does increase in value, but each time that you get into this blue region over here, there's a significant jump. Now for sodium, it was because we jumped into a stable state and then we tried to remove 1 extra electron. But why is there a increase for that third one for magnesium? Why is that one so much more? Why wasn't it with the second one? Let's take a look at magnesium and why it does that. All right, so we're done with the sodium. So if we have magnesium, magnesium is going to be the next element on our periodic table, element number 12. So if you have 12, still on that third energy level, but this time it's not going to have 1 outer electron, it's going to have 2. So for magnesium, it has 2 valence electrons right now, and that means that it's unstable. For it to become chemically stable, we'd like to have 8 valence electrons. So we need to start removing electrons. And in order to remove electrons to form a magnesium ion, we have to apply some energy. So the first one I'm going to take away is that one right there. So this one right here, we're going to have to apply the first ionization energy to remove that. All right. So when we go to remove this outer electron, okay, so I'm going to get rid of that. How much energy is needed to do that? Well, we go to our periodic table, or I'm going to cheat just a little bit. I'm going to look at this. We have 738 kilojoules. So we'll write that down. The first ionization energy, 738 kilojoules per mole, is going to be needed to remove that first electron from the magnesium atom. Now the second one, it's still unstable. We've reduced our number of valence electrons from 2 to 1, but it's still unstable because it still has 1 outer electron, and we don't want 1, we want 8. So that brings us to the second electron that we have to remove. This guy right here, we need to get rid of it. Now since it's the second electron that we're removing, second electron, we're going to need to apply the second ionization energy. So how much energy is going to be needed to take this electron right here and pull it away from magnesium? Well, we go to our list. Our list says that in order to remove that second electron, we need to apply 1,450. So 1,450 kilojoules per mole to remove it. All right, so again, we removed that electron. Now, when we do that, when that second one is removed, now we have 8 valence electrons. You go from that thing being unstable to now it is stable. Since we did form an ion, we should put the charge of what it is. We lost 2 electrons, so we'd become more positive by 2. All right. Now, let's do one last thing. If, for whatever reason, we'd like to get rid of that electron right there, okay, what would we call it? That's the third electron that we would try to remove, so that's the third ionization energy. Now, if this element right now, this magnesium ion, is chemically stable, that third electron is not going to want to come off of there. 1, it's stable. 2, as you start removing these electrons, that radius, remember that when you take and remove electrons, that atom keeps getting smaller and smaller. So that third electron, not only is it in a stable state, but that third electron has moved closer and closer to the nucleus, making it more difficult to remove. The energy needed to remove that third electron, that third outermost electron, the one that would be one of our core electrons, you're looking at 7,730 kilojoules. So for us to grab this third one right here and pull that thing away, we would need 7,730 kilojoules per mole. All right. Now, because magnesium doesn't want to do that, I'm going to put that thing back. That was just to give you an idea. If we wanted to, we could, but each time that you remove a successive electron, that radius decreases in size. The outer electron comes closer to the nucleus, and it becomes harder and harder and harder for that each successive electron to be removed. Okay? All right, so let's wrap this up then. If we go to our periodic table, and mine's right up here, let's make sure that you put in these little helpers so that way you can refer back to what those trends are quickly and not spend a whole bunch of time trying to hunt down or remember what's going on with it. You should have, from left to right, right now, that the radii decreases. Now, if you don't have any of these on your paper, you want to make sure that you do get it down. As you go from top to bottom, the radii increases. All right. Today, what we looked at was the ionization energy, so I'm going to abbreviate that IE. As we move from left to right across the periodic table, since the radii is decreasing, that means that the electron is closer to the nucleus, and each time that that electron comes closer to the nucleus, it becomes more difficult to remove, so more energy is needed to pull it away. So our ionization energy increases. On our ionization energy in terms of our groups, if the electron is further away from the nucleus, that electron is going to be held looser. It's not going to be as difficult to remove, so our ionization energy is going to decrease. We should also have our radii for our ions. So remember that as you move from left to right, as you have a metal that's losing electrons, that radius is going to get smaller. And then on the right hand side of the periodic table, the radius of your anions, those are going to get bigger as you add more and more electrons to it. All right, so that should be all you need for the homework or classwork. You might be able to get it finished up before you leave. But it's the 2-page paper. On one side, it's just a review of the atomic radii. And then on the back side of it will be the ionization, a few questions related to what we looked at today or what you should have read in your textbook. All right, see you guys on Monday.